Good morning, ladies and gentlemen. Welcome back to a new lesson. Our lesson today is about electron configurations. Okay. Before we learn about the Bohr model, and the Bohr model is electrons go on rings, if you recall, and then the electron cloud model is the modern atomic theory. The modern structure of the atom is the electron cloud model. The electron cloud model says that electrons are in clouds, not specific rings, and these clouds, ladies and gentlemen, are actually, let me move this over. These clouds are actually what we call orbitals. Okay, orbitals are how electrons fill in. Oh no, this is so. You can't see that. Let me pull this up real quick here. Okay, they're in orbitals here. Let me minimize this a little bit. So in orbitals are labeled. Look here on the screen, 1s, 2, and then the next level is 2p, and then 3s, 3p, 4s, and then under 4p is 3d. See, you just go up the ladder, fill it up by increasing energy. The more energy means the further away they are from the nucleus. The more energy means the electrons are further from the nucleus, less attraction from the nucleus. Okay, so 1s, 2s, 2p, go up the ladder, 3s, 3p here, 4s, 3d, 4p, 5s, 4d, 3, 5p, 6s, 4f, 5d, 6p, etc., etc. So, do you have that remember already? Of course not. So let me go over how to use that. Okay. So you should have this as far as your notes go. You saw S, P, D, F, and then the number in front. Okay. And so the S, what it is just a shape. Sublevel, the shape of that is a sphere. So you see here a sphere, and it has one orbital, and if each of it can hold 2 electrons, so S can hold up to 2 electrons. Maximum electrons 2. So for S you'll see a 1 or an S2. Alright. P, there's 3 of them, so it can hold 6 electrons. Remember, times 2. Each orbital can hold 2 electrons. The P here is like a dumbbell shape. The P is like a dumbbell shape, but it's like 3D, so you have 3 dimensions, X, Y, and Z, for example, three dimensions. So it's more 3D. So you have, it looks better here. There's probably a better picture online. It doesn't print out really well here, but just know that P can hold 3, and so P can hold anywhere from 1 to 6 electrons. P1, P2, P3, P4, P5, P6. It won't make any sense now, but it'll make sense when we go over some examples later. D has 5 orbitals, so times 2, that can hold 10 electrons. F, 7 orbitals, can hold 14 electrons because 2 per orbital. Okay, orbital. Sublevel is the letter, and the orbital is the actual location of each electron. And remember, it's electron cloud. We don't exactly know where it's at or how fast it's moving simultaneously. That is the Heisenberg uncertainty principle. So earlier when I mentioned the order of those things, let me pull that up again. The order of these things, look, 1s, 2s, 2p. See, you don't have to memorize it. We have this thing called the diagonal rule. That diagonal rule works as follows. So you start from this line here, this pink line I'm drawing here. So you start from that line, you go back to that line, you go 1s. It's called diagonal rule, so we're not going to read it left to right. Okay, do not read it left to right. You have to read it diagonal. It's called a diagonal rule. Diagonal rule. 1s, and then after 1s is done, you go back to the line, go 2s. So it's 1s, 2s. After 2s is to go back to the line, 2p, and then 3s. See, up to this point, if you read left to right, it's the same, but after this point, it's not going to be the same. So 3s, after 3s is 3p, and then 4s. So 3p, 4s, 3d, 4p, 5s, 3d, 4p, 5s, and then 4d, right? You go continue 4d. I'm going to use my left hand here. 4d, 5p, 6s, 4f, 5d, and 6p. 7s, 5f, and then 6d. Goes like that. And then 7p. So that's the order of that. That's how you read that in order. Sorry, look at my left hand. It's not really that good. But there it is. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. Remember, go back to the original. So go back to the end. Follow the arrow. Go back to the end. Follow the arrow. Go back to the end. Follow the arrow. Okay. So as you read it, you see like 1s is the first row. The first row only has 2 electrons. 1s1, 1s2. Second row, 2s. Second row is 2s. Third row is 3s. So the number in front corresponds to the row number, the shell number. So there's 7 rows. It only goes up to 7. The s is a subshell or sublevel. Possibilities are s, p, d, or f. And the little bitty number up here is the number of electrons. Remember, s can only hold 2. You're not going to see s. You can see S1, S2. You're not going to see an S3 or S4. It cannot hold 3 or 4. It can only hold 2. Once that's full, you go to the next one. All right? So down here is just another quick practice here. 2s can hold how many electrons? So just look at the letter. S can hold, how many electrons can each of the following hold? S can hold 1 to 2. Okay? F can hold how many? 1 to 14. 14 max. D can hold 1 to 10. You can have D1, D2, D3, all the way to D10. Not D11. It can't hold D11 because there's only 5 D levels. Orbitals, I'm sorry. P can hold 1 to 6 electrons. And D here, again, 5 orbitals. It can hold up to 10, so it's anywhere from 1 to 10 electrons. And so how does this apply to anything, right? So here it goes. Here's how we write electron configuration. Electron configurations is basically an address to tell you where electrons are, where they may be. Well, they're in there, but we don't know exactly where the possibility of where they're going to be in the atom. Okay, so here we have, for example, hydrogen. So we determine the number of electrons and we fill them in. Hydrogen is 1 electron. Yes, 1 proton, 1 electron. These are all neutral. There's no charge on there, so the number of proton is equal to the number of electrons. It's a neutral atom. Okay. So if it's 1 electron, so we just fill in. Remember, the order is this. We only have 1 electron, so we're going to fill in 1s1. That's it. 1. We start 1s1. That's all. That's the address for that one for hydrogen. So for helium, it has 2 electrons. So we always start with the first shell, the lowest energy level, 1s. Now we have 2 electrons, so we have 1s2 for helium. Lithium has 3. It's a little change here. So 1s, you can't just put 3 on the s because s can hold how many? S can only hold 2. So this is 1s2. I almost made that mistake. 1s2, and then now what's after 1s? 1s2 is full. Okay, well, we go to the next one, 2s. 2s, and then we'll have 1 left. So the little bitty number up here, the superscript up here, needs to add up to the total number of electrons. Okay, you just fill it up until you reach that number. So beryllium, continue. Beryllium has 4 electrons, so we go 1s2, 2s. We need 2 more, 2. So then that's 4 total electrons. All right. It's not so bad. It just takes a little bit of practice. This is new. So look, magnesium, atomic number 12. So magnesium's 12. So we go 1s2. That's full. Go to the next one. 2s2. That's full. After 2s is, look, diagonal. 1s, 2s, 2p. Right? If you write it out like this already, it makes it a lot easier as well. So after 2s is 2p. P can hold 6. Notice that's 6, 2, 6, that's 10. We need 12. Okay? We need 12. So we need 2 more. What's after 2p? 3s2 is your last 2 electrons. There goes 12 electrons. Okay? Yes, it does get harder and harder because as we go down the periodic table, there's going to be a lot more electrons. Okay? So Fe here, for example. Fe is atomic number You can't see that far. Don't have it. Remember, 26. 26. So go 1s2. 2s2. What's after 2s? 2p6. That's 10 electrons. We need 16 more. 3s2. That's 12 electrons. Okay, 2, 4, 10, 12. We need 26. 12. 3s is after 3p. 3p6. Now that's 18. 4s2. Remember, s can only hold 2, so that's 20. And then 3d. How many do we have? We need 6 more. 3d6. And voila, that's our electron configuration for iron. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Guys, don't write commas in between, don't write hyphens, don't write dashes in between. Just make sure your big number, your front number, your principal quantum number, that's the first number, is your big number in front. Make sure it's a big number. It clearly shows it's a big number. And the subscript, the number of electrons, is a subscript. Okay, so the way we write this is fairly important, so that there's no confusion. Okay, so sulfur, one more here, 16. It's a little easier. It's less. 1s2, 2s2, 2p6. That's 10. 3s2. That's 12. And then 3p. We only need 4 more, so 3p4. There you go. There you go. 3p4. Okay, so that's how we do that. Electron configuration is fairly simple, and always have the diagonal rule with you. Always have the diagonal rule. See here. So on the next page you'll practice that. Okay, on this page you'll practice all these. We've done a lot of these already. So let's say for uranium, let's look 92. That's a fun one. That's a fun one. All right, so we go. Here we go. We're not going to finish unless we start, right? 1s2. 90 left. 2s2. What's after 2s? Go back to diagonal. 2p. After 2s, it's going to go back to line. 2p. 2p6. Okay, after 2p is 3s2. 3p6. 3p6. And then after 3p is 4s2. And then 4s. After 4s, remember, if you're reading diagonally, so if you read left to right, it'll be 4p, but no, we have to go back to the line. Go back to the line. It's 3d. 3d after 4s, which is 3d10. 4p6. 5s2. Go back to the line. 4d10. 5p6. It's 92, so I'm going to go for a little bit. I'm going to add up a little bit. 4p, 5p6, 6s2. Okay, we can add now. 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 50, holy smokes, 54, 56, oh boy, it's only 56 so far. 6s, what's after 6s? 6s is here already. Just follow the map, right? This is your map, 4d, 5p, 6s. 4f, hey, the 4f is nice because we get to jump 14 electrons. 14. That was 56, that's 70. Hey, that's 70 up to this point.